associated socio-economic impact. Both wet and dry events are interconnected with same hydrological processes and atmospheric dynamics. So we need to study together uh, for the better understanding of the transition dynamics. Celia have already experienced disaster related to rapid transition. My study area is Indian part of Upper Indus Basin, which have a complex geography. Graded Aphrodite daily data is used at 0.25 degree by 0.25 degree resolution for 1961 to 2014. We have tried to find out the climate change in influence on transition, compared the event transition from wet to dry events and dry to wet event, average transition time between dry and wet spell. Finally, check the hosting of hotspot for the rapid wet dry events in Upper Indus Basin. Study, we have used the SPEI value to decide the events as extreme, severe, or moderate type of wet and dry event and normal event. Along with this, we have used wet dry ratio, wet dry transition time, wet dry rapid transition events. For checking of trend, we have considered number of wet and dry months every year. In bar chart, W stands for wet and D for dry, M for moderate, S for severe, and E for extreme. We observed before 1996 more dry spells was there, and after that we wet spell. After 1996 it's yellow and red, and before that it's blue and green. That's why it's drought and it's wet. In 1996, ENSO affected this area much, and similarly in the SPEI 12 figure we can see the same thing. There is a higher SPEI value after 1996 and lower in before 1996. We can see the more sensitivity in SPEI 1 compared to SPEI 12, 6 and SPEI 3. So we have used SPEI 1 for the further study. You can see there in the three figure, moderate, severe, and extreme. In wet to dry ratio greater than 0 implies the prevalence of wet event, and less than 0 implies dominance of the dry event. In case of moderate spell, UIB has almost equal number, but as the severity is increasing, wet events spells number is increasing. Middle part of the basin is getting more wet spell than dry spell, and when severity increases, the wet events are increasing. A figure in wet dry transition time. First is number, second the average time between the transition. The upper part of the basin is more frequent in transition from one extreme to another, and there are some other area which are becoming the hotspot in this area. The middle part of the upper boundary is becoming the hotspot and transition in extreme event. The transition time for the dry wet spell is relatively lower than the transition from the wet to dry. Rapid transition events are those which having 1 month as a dry event or wet event, and the frequent next month will be the opposite month. That will be the rapid transition events. These events are seen in much in number in some areas, like 18 to 20 times in this area, and this middle part for the dry to wet. And similarly, these are high in this area for wet to dry, and it's a little bit high in this area also. So these are the area where rapid transition are prominent there, and should be considered for future planning of water resources. Thank
Thank you, Dr. Arya.
you so much for joining me.
We will go to our second speaker, which is Dr. Paula. The presentation is about alongshore upwelling modulates the intensity of marine heat waves in a temperate coastal sea. It is also a virtual presentation. Let me play the video.
Good afternoon. My name is Paula Izquierdo, and I am a Biogeosciences PhD student at the University of Oviedo. Today, I would like to introduce you to one of my thesis latest research titled "A Longshore Upwelling Modulates the Intensity of Marine Heat Waves in a Temperate Coastal Sea." Marine heat waves are transient episodes of extreme water temperatures that have detrimental and long-lasting impacts on marine ecosystems and cause the loss of valuable goods and services from the local oceans. Within the past few decades and under the influence of anthropogenic climate change, marine heat waves have increased in frequency, intensity, and duration, and future projections point towards an increase in their likelihood and severity around the world in the coming years. High data demands make most marine heat wave studies to rely on satellite datasets and to focus on open ocean pelagic environments. In coastal areas, however, the presence of land and local processes like coastal upwelling limit these approaches, which can affect the detection of marine heat waves and raises concerns about their actual impact in upwelling-sensitive coastal areas. In our work, we analyzed the incidence of marine heat waves along the coast of the Cantabrian Sea, a temperate shelf sea in southern Bay of Biscay. First, we assessed the reliability of satellite products to accurately retrieve near-shore sea surface temperatures. We did so by comparing 20 years of sea surface temperature data retrieved via satellite products and field measurements from two selected coastal locations, Oleiros and La Franca. The analysis revealed large deviations between field and satellite temperature records, which increased during the upwelling season between April and September at both locations. Here you can see the results for the year 2005 as an example. In general, the satellite series is smoother and lacks sudden temperature fluctuations associated with upwelling events, which are instead reflected in the field record. To reconcile both approaches, we developed a statistical downscaling approach based on regression modeling, which allows to obtain finer scale projections of climate variables affected by local processes not captured by coarse resolution products. I won't go into detail so as to adjust to the time limit, so I'll just point out that including the effect of cross-shore transport and air-sea heat fluxes as a proxy for seasonal stratification in the model enabled us to predict an improved temperature series that reliably reproduces near-shore sea surface temperatures, retains the satellite's spatiotemporal resolution, and improves marine heatwave detection near shore. We first used the model to reconstruct coastal sea surface temperatures at both Oleiros and La Franca between 1998 and 2019. As expected, the modeled series amended biases between field and satellite records due to seasonal cross-shore transport. You can see here the comparison between the sea surface temperatures from each approach at Oleiros and La Franca in 2005 again. We then used the downscaling model to exploit the prolonged spatiotemporal coverage of the satellite record and predict an improved coastal sea surface temperature series spanning the last 4 decades along the entire Cantabrian coast, which we took advantage of to assess the role of long-term ocean warming in the incidence and characteristics of marine heat waves. To achieve this, we extracted marine heat waves using a static versus a dynamic detection threshold, which allowed us to contrast marine heat wave trends with and without the effect of long-term ocean warming. Our analysis pointed towards a potential role of long-term ocean warming in enhancing the incidence of marine heat waves in the Cantabrian Sea in the past 40 years. On average for the entire Cantabrian coast, this is the number of marine heat wave days per decade detected using a static and a dynamic threshold. This may be interpreted as 80% of marine heat wave days taking place regardless of the underlying warming trend and the remaining 20% occurring because of it. The proportions increased to a 60-40 for the period from the 2000s to 2019 and to a 50-50 between 2010 and 2019. That is, during the last decade, half of the marine heat waves detected along the Cantabrian coast occurred under the influence of the ocean warming trend. Our study calls for full risk assessment of the Cantabrian Sea marine organisms and ecosystems in order to encourage the elaboration of appropriate conservation and management strategies for a warmer future. The approach presented here might contribute to improve the monitoring of the impact of marine heat waves on coastal marine ecosystems, which remain key for human livelihood but are currently endangered under the threat of escalating global warming. The results of this research have been published in the journal Science of the Total Environment under this reference. In case you have any questions, you can email me to this address. Thank you for your attention.
Thank you. Our next speaker is also virtual. So by Dr. Athira. The presentation is about analysis of cold waves over North India, climatology, trends, and synoptic dynamics.
Good afternoon, everyone. I'm Adira KS from Indian Institute of Science, Education and Research, Mohali, India. Today, I will be presenting on the analysis of cold waves over North India. Cold waves are key type of extreme weather events, which is associated with extreme low temperatures and incursion of cold, dry winds from the northern latitudes into the subcontinent. These are driven by synoptic scale processes and has a wide impact on the human society. As you can see in the figure, the cold waves mainly affect the areas which are to the north of 20-degree latitude. Cold waves are characterized by a sharp drop in the air temperature, which can go to extremely low values, a steep rise in the pressure, strengthened wind speed, and associated weather events like frost and icing. The main objective of the study is to identify the extreme cold wave events over North India and to study the synoptic dynamics. To identify the extreme cold wave events, first of all, we have considered the climatology of the minimum temperature from 1982 to 2020 during the winter season. The North India shows a minimum temperature less than 12 degrees Celsius. Also, there is maximum variation of the minimum temperature during the winter season. Considering both these facts, we have considered the North Indian region for the identification of cold wave events. The extreme cold wave events are identified when the normalized minimum temperature anomaly is less than -2 standard deviation for 4 or more days. To study the synoptic dynamics of the extreme cold wave events, the composite anomalies of various parameters are carried out. The surface air temperature shows negative anomalies over parts of the North India, which is less than -3 degrees Celsius. Also, the prevalence of northwesterly winds. The mean sea level pressure shows the higher pressure systems over the northern latitudes and anomalous low pressure systems over the northern Pacific. This pressure gradient helps in the enhanced northerly winds from higher to lower latitudes. The meridional wind pattern shows negative anomalies over parts of India extending from Siberia. This shows the northerly wind component associated with the extreme cold wave conditions. The geopotential height at 200 hectopascal shows a ridge over the Ural-Siberian region, which is flanked by 2 troughs. Also, there is an anticyclonic circulation. This is a representation of an omega kind of blocking. The downstream portion of the block carries cold northerly winds from the higher latitudes into the subcontinent, and the southerly winds carry the warm air from the equator towards the higher latitudes. This can also be seen from the temperature advection at 850 hectopascal, where the negative anomalies shows cold air advection over the northern parts of India, and at higher latitudes we can see the warm air advection. We have also computed the ED growth rate for the extreme cold wave events. ED growth rate is a measure of baroclinic instability. It is dependent upon the meridional wind component and also the vertical wind shear. We can see higher values of ED growth rate over the northern parts of India. This represents a higher baroclinic instability associated with the cold wave events. Lastly, we have also looked into the trend of the cold wave events. The first figure shows a spatial map of the trend of the frequency of cold wave events. A significant decrease of cold wave events is observed over parts of Rajasthan. Overall, there is a significant decrease of 0.6 events per decade over the entire northern parts of the country. Similarly, the duration shows a decreasing trend over most parts of the northern regions. A significant decrease of 3.5 days per decade of the duration of cold wave events is observed for the entire North Indian region. The intensity also shows a decreasing trend over parts of Rajasthan. Overall, there is a significant decrease of 0.23 degrees Celsius per decade for the intensity of cold wave events for the North Indian region. Coming to the summary and conclusion, we have studied the extreme cold wave events over parts of the North India during the period 1980 to 2020 during the winter season. The Ural-Siberian block favors extreme cold wave events to occur. There is an anticyclonic circulation associated with the block, the downstream portion of which carries cold northerly winds into the subcontinent from the higher latitudes. This leads to extreme cold wave conditions over the country due to the cold air advection. To sum up, we show that extreme cold wave events are strongly linked to different large-scale circulation patterns such as the Siberian high-pressure systems. These extremes can vary in the number, duration, and intensity each year. These are some of the references. That's all about the presentation. Thank you.
Thank you, Dr. Athira. So the next presentation is by Dr. Muhammad. The presentation is about beyond mean and variance, rapid and extreme day-to-day changes in temperature across the contiguous United States. Please.
Yeah, he's on the PC, right? He's on the PC.
Right. Good afternoon, everyone. So today I'll be talking to you about a slightly distinct kind of extreme events which relate to day-to-day changes in temperature. So first of all, day-to-day changes in temperature have significant implications on human health. This figure here is from a study that looked at the relationship between daily temperature changes and non-accidental mortality across the US. And you can see that higher percentiles of daily changes in temperature are associated with a higher risk of mortality. There are also several other studies that reach similar conclusions. Now, despite of its importance, this kind of extreme events is not included in our basic definitions of extreme events. This is a figure from IPCC AR6, which shows different categories of climatic impact drivers. And among those, we don't see daily temperature changes. So I will be referring to day-to-day changes in temperature as temperature volatility for the remainder of this talk. Now, in this study, we were interested to examine patterns of temperature volatility across the US. And we specifically started by using 1,500 stations from GSCN dataset. So this map here shows the climatology of extreme volatility from 1950 to 2019. You can see there is a very coherent spatial pattern with high values of volatility over the Great Plains region and low values over the west and southeast west of US. I would like to draw your attention also to the scale of values here. So a lot of these stations have temperature volatility exceeding 10 degrees Celsius, reaching values as high as 12 degrees Celsius, which is a very significant change of temperature from one day to another. We have also looked at whether those volatilities are associated with a decrease or an increase in temperature. And this map shows that for the majority of stations, extreme volatilities are actually associated with a decrease in temperature. Another aspect that we have examined here is the timing of those extreme volatilities. And this map here shows that there is, again, a very coherent spatial pattern for most regions in central and eastern US. Those extreme volatilities typically occur during the winter season, whereas for the western part, they typically occur in late spring and early summer. Of course, it is also important to look at trends. So this map here shows the statistical trends as estimated by the non-parametric Mann-Candle test. The size and color of markers here is proportional to the magnitude of trend. And we can see that there is a very robust regional pattern with a statistically significant increase in trends over central and eastern parts of the US. If we aggregate those trends for different regions, we can see some of the differences more clearly. So here we can see that there are certain regions such as the Northern Rockies or the Upper Midwest that have either higher percentage of stations with increasing trend or higher magnitude of trends. And overall, these trends ranges from 0.2 to 0.35 degrees Celsius per decade. Finally, we were also interested to look at or compare the reanalysis data sets with observations. So here I'm showing you two maps from ERA5 and NOAA 20CR for their estimates of extreme volatility climatology. And we see that both reanalysis data sets underestimate the climatology observed in GHCN dataset. We can see this more clearly here in the scatter plot with NOAA 20CR in green color, ERA5 in blue color. More importantly, the trends from both reanalysis data sets are also quite different from GHCN. And actually, they show opposite trends, which is very, very interesting. So before I wrap up here, just to summarize the main findings, first of all, temperature volatility is very important kind of extreme events because of its significant implications on human health. We have seen that there are statistically significant increasing trends over central and eastern United States, and this poses a question of whether this can be attributed to anthropogenic global warming. And finally, reanalysis data sets seem to underestimate climatology of extreme volatility and also fail to reproduce observed trends. And this poses the question of whether this can be attributed to deficiencies in numerical weather prediction models. So if you are interested in more, you can look at this paper that we just published in Weather and Climate Extremes. Thank you so much.
Thank you, Dr. Mohammed. So I would like to request all the participants, if you have any questions, please use the online platform. You can write the questions or you can write down your questions so that we can take it during the discussion time. So I would like to move to the next presenter by Dr. Zhang. So she will talk about constructing responses of hailstorms to anthropogenic climate change in different synoptic weather systems.
Hello, everyone. My name is Yue Zhang from PNNL. My topic is contrasting responses of hailstorms to anthropogenic climate change in different synoptic weather systems. A severe convective system always produce weather hazards like heavy precipitation and hail, which will cause significant economic loss. However, our understanding of how anthropogenic climate change impact the severe convective storms characteristics is very low. So our objective is to first to see how the hailstorms will respond to the climate change. And our focus is on the central US, and we find that the hailstorms occur in central US is usually associated with the two major type of synoptic scale environments. One is the frontal system, which is associated with a strong middle level trough. Another type is the Great Plain low level jet, which is characterized by the broad and extended low level moisture transport. So here's our second objective is to see, do the hailstorms associated with these two different types of synoptic environments will respond to the ACC similarly or differently. So we run the simulation using WRF model coupled with NSSL microphysics for forecast for each type at 1.2 kilometer resolution. And for the future scenario simulation, we use the procedural global warming, which is PGW approach. And what we find is that the frontal type has over 110% more high or more larger hail, while the JPLJ system has much less sensitivity to the warming, which is only about 20% increase. And when we see the pre-convection meteorology, and we find that only pure this alone, it can hardly to explain why these two different environments has a different sensitivity to the ACC. So, but later when we look into the cloud dynamics and also warm cloud depths, they do explain the different responses, which is showing here that we find that the frontal system has larger increase, which is from black to the red line. We find that there has a larger increase in updraft velocity and also updraft width. And in the meantime, we also find that for frontal system, it has smaller increase in the warm cloud depths. So both of these is favorable for the more supercooled liquid above the melting level, and the future it can grow into graupel or hair through the freezing or ramming process. And I think our study has the impact that by linking the ACC impact on hailstorms to the synoptic scale features that are easier to model. The study also advanced our knowledge of hailstorms predictability. The concept can be used to facilitate the studies of climate change impact on hail in other hail-prone regions. And if you would like to know more details, you can go to see these references, and this study has been published. Thank you.
Thank you, Dr. Zhang.
So we can order it.
So the next presenter is a virtual one. It is by Dr. Chandrima. The talk is about, does moment of microphysics parameterization schemes have any impact in simulating the lightning events?
Hello everyone, I am Chandrima Malli. I am doing PhD at IITM Pune. First of all, I would like to thank AGU very much for giving me the opportunity to present my work in this platform. Now coming to my presentation, today my topic is, does moment of microphysics parameterization schemes have any impact in simulating the lightning events? Now, why the simulation of lightning is important? We know lightning is a major hazard which kills so many lives throughout the world. As per statistics, almost 2,300 Indians die every year due to it. Even it causes more casualties than the other natural disasters like torrential rainfall or landslides over India. Similar picture we can see over other countries, for example, USA, South Africa, and so on. Recent study by Indian Meteorological Department reveals that lightning deaths has been doubled since 2004 over India. Now, let us look into what are the challenges and what may be the way out. We know, according to the non-inductive charging mechanism, the collisions between groupal particles and cloud ice crystals cause charge generations in the presence of supercooled liquid water. But the widely used double moment scheme has simplified representation of spherical ice crystals with a fixed density, which can lead to large uncertainties in the model. In this scenario, we are considering the triple moment scheme from National Taiwan University, which additionally contains the shape information. In the present study, I have compared the Morrison double moment and NTU triple moment scheme to simulate lightning in WRF model. Now, to check whether this scheme can really capture the shape information, the model fidelity test have been performed firstly. The radar reflectivity is shown here for the thunderstorm case, and the different types of cloud hydrometeors from KIPEX observation is shown here. From the model, the ice aspect ratio, that is the C by A ratio, is plotted for the same event, And we can see that spherical, columnar, and plate-like structure of flight hydrometeors is well captured using the third moment scheme. Therefore, with this scheme, the three different types of shape information can be incorporated in model. Next, we have considered different lightning events over eastern part of India. The first case of 3rd May 2019, the observation data from IITM Lightning Detection Network is shown here. The lightning potential index for both Morrison and NTU triple moment scheme are obtained, and we can see here that Morrison scheme simulates more LPI than NTU. Next, we have seen what is the distribution of rainfall. Although the Morrison scheme simulates more rainfall than the triple moment scheme here, we can see that both the schemes more or less captures the observational pattern of the 24-hour accumulated rainfall obtained from satellite. Now, while the Morrison scheme is producing more rainfall, one answer might be we can see in the middle level of vertical profile of cloud hydrometeors, particularly around the 500 HPA. This cloud hydrometeors is more in the Morrison scheme than the NTU. Also, interestingly, the NTU scheme can capture the distribution of cloud hydrometeors in the upper level more. Now, if we look into the time-height profile of reflectivity over a region where intense lightning was observed on that day, it shows more strength in the triple moment scheme. The temporal evolution of maximum reflectivity also differs in these two schemes. For the next case of 25th May 2019, only the lightning potential index is shown here. Here we can see that the Morrison microphysics scheme is producing more LPI over some regions like the previous case. The other parameters has also shown similar results, but it is not shown for the brevity of presentation. However, the results are in line. Therefore, we can tell that the simulation is sensitive to the choice of double moment or triple moment microphysical parameterizations. And this new generation triple moment scheme might be more useful in simulating the lightning in model. I again thank the AGU and thanks audience.
Thank you, Dr. Chandrima. So next speaker is Dr. Christiana, and the talk is about changing temporal volatility of precipitation extremes due to global warming.
Okay, welcome everyone. I'm going to talk about temporal volatility of precipitation extremes. And by this, I mean two things. First is the waiting time distributions. Here I just show two examples. Waiting time, I mean the time between consecutive precipitation events. And then we just look how often we have to wait 1 day, 2 days, 10 days, or 20 days. And here two different grid points, say for the ERA 5 data set. So we see just here two different distributions. One, which the waiting time distribution decays relatively quickly, and one where it decays much more slowly. And to quantify this, then if those events would actually occur independent from each other, then we would have an exponential waiting time distribution that could be represented by a Poisson process. But if we don't have an exponential waiting time distribution, that means there might be actually some correlations between the times, and we can get also much longer time periods without any events to occur. So I look at ERA 5 data, but also at the CSM simulations where we have a control one with present day levels of CO2, which I call here 1 time CO2, and then I compared this with a simulation with 4 times CO2. And the other quantity which we can look at for volatility is basically the clustering of events. So again, the idea is not all extreme events occur independent from each other. There might be some correlation, some dependence in time. So, and very often, if we look at extreme events, precipitation is here, or temperature, or any other climatic relevant variable, then we fit some extreme value distributions. And here I just illustrate this, whether we kind of assume that all events would occur independently. So that's the solid line, or if there would be some kind of clustering occurring. So if you're aware of extreme value statistics, then typically if there is clustering in the data, then we would actually decluster the data. And so that also would kind of affect the probability density distribution. And here you can also see, if you then compute the extreme index, which characterizes the clustering, then that would then also have an impact on the probability distribution, or here on the corresponding return levels. Okay, so first, waiting time distribution quantification. Here I use the fraction Poisson process. That's a parameter which has values between 0 and 1. If they're 1, then basically this corresponds to the traditional or the standard Poisson process. And if we go towards values of 0, so basically that means that the dependence of the events is much larger. So here you can see this for ERA5, CSSM, and here the difference between the CSM simulations 1 times versus 4 times CO2 levels. And you can see here significant changes in the waiting time distribution, which we can expect in the future climate. So the other measure, the extreme index for clustering, again, this has values between 0 and 1. 1 means that all extreme events occur independent from each other. And 0 means there would be very, very strong correlation or dependence between subsequent extreme events. And I display here only values which are significantly significant, or those gray areas that are not significant. And you can also see here most values are somewhere between 0.5, 0.6, so there are also some clustering going on. And also ERA5 and CSM, they have relatively similar pattern. So that means that the model actually performs relatively well. And also, again, if you look here, the difference between present day clustering versus future clustering, then we can also see here significant differences, which we can expect in the future. So far, I always looked at or showed you how this looks in the winter season, December, January, February, and here just to show you that we can also see differences, also seasonal differences in, say, clustering between here the winter season, DJF, and JJA. Okay, I'll probably run out of time here, just my summary. So I showed you some significant evidence that we can see some power load distribution of waiting times between precipitation extremes and also serial clustering of precipitation extremes. And using CSM and relatively high resolution and present day level CO2 and 4 times CO2 levels, there we see that we can kind of see significant changes in the waiting times, which become actually shorter, and between clustering, which kind of increases. So that means that the global warming will also affect the temporal characteristics of precipitation extremes, so that they become more volatile, which then also has some impact or some implications for impacts. So if that's, of course, very fast explained everything. So that's also published in this paper here in the International Journal of Climatology. Or if you have more questions, then maybe just talk to me after the session. Thank you very much.
Thank you, Dr. Christina. So the next speaker is by Soumya Singh. His talk is about future projection of changes in heat waves over India using Codex South Asian RCM ensemble. Recorded?
We may not have it, sir. I wasn't able to check that because I was. We may have to skip them. Is he in the room even?
I think no.
He's not even here, so. You're supposed to know these things. Not even here, so maybe that's why I just texted the speaker ready room. They don't have anything for him. He said, can you ask if he's in the room? Is
Soumya
S
Singh
Singh in the room, the
in
next
the room?
speaker? I guess not. Okay, thank you.
Okay, then we will go to the next one. We'll sort it out later. So the next is by, it is also in person. So it is by Dr. Zhang. So the talk is about heat wave predictions with dynamical and statistical downscaling methods. Okay.
Hello, everyone. My name is Leyuan Zhang. I'm a PhD student in the University of Tennessee. Today, I'm going to talk about the downscaling methods accurately predict heat wave risk in the changing climate. This work is, I work with my group member, Hannah. As the weather records, there's unusual high temperatures in the summer of 2022, which caused financial loss, health impacts, and glacier ablation. It is well accepted that climate change has increased the frequency, intensity, and duration of the heat wave. But the problem is the predictions of the regional specific research from heat wave, it has not yet well qualified. So there are a lot of heat wave index research have used. For our research, we choose the heat wave magnitude index, which is HWMI in this research. The data we use is the CMIP6 model with 6 hourly data under the SSP5 RCP 8.5. It was downscaled from the 18 kilometer to 4 kilometer. Use both a dynamical method, which is a regional climate model system, REGCM4, and the statistic approach, which is a double Bayes correction constructed analogous, which is DBCCA. So the evaluation dataset we used was a DMAT. It is a set of 1 kilometer horizontal resolution data. So based on this, we explored the difference between the dynamical and statistical downscaling techniques and examined the heat wave characters in the future. This figure shows the characteristic of the heat waves for the DBCCA and REGCM4 compared to the DMAT data during 1980 to 2019. When you look at the lower percentile threshold, the REGCM4 estimates are closer to the DMAT data than the DBCCA, especially for the HWMI and the duration. This figure shows the trend of the heat wave characters by 4 different percentile threshold and 3 different reference windows. We can see from the figure, the REGCM4 shows the average star day will occur earlier each year, which means in 2020, the average star date across the US is around day 200 during mid-July. But by 2059, the date will have shifted closer to day 175 in late June, which shows almost a whole month earlier. This table is a k-test for compare the distribution of DMAT, HWMI to be scaled heatwave advisory warnings from the NWS. We can see from the table in different area, the threshold, the compatible threshold is different. But for the whole US, it is the 95% threshold, which is most similar. This two figure shows the average minimum daily temperature trend and the average seasonal temperature trend separately. We can see that in the Northeast, North Rockies, Ohio Valley, South, and Upper Midwest, DMAT data shows little to no increase in overnight temperatures, but the model examples predict increase. So we can see from the right figure, the interannual variability is now consistent between seasons and throughout the year in the example models. So it is obvious that the dynamical downscaled method, RGCM4, are more reliable at predicting the heatwave rates. So for future work, we plan to do some work about multi-model examples of dynamically downscaled models and investigate the difference between winter and summer heat waves in terms of human and environmental health. Thanks for your attention.
Thank you. Thank you, Dr. Zhang. So we will move to the next speaker, Dr. Michael. The talk is about how high-resolution models better represent the atmosphere. Oh. It's fine.
All right. Hi, everyone. Yeah. So my name is Mike. I'm a PhD student at the University of Toronto, and I'm going to be talking about some of my work about extreme winds in Canadian cities and how they're represented in climate models, as well as with high resolution. Right. Yeah. So some motivation. So extreme near surface wind speeds are a major natural hazard. They can cause a lot of damage, like we've seen, like is shown in this photograph here from a derecho show that hit Toronto back this past spring. So this is a particularly severe event. You can see a lot of the, knocked over trees, down power lines, damaged people's homes and vehicles and whatnot. So because of the impacts that these extreme wind events can have, it's important for us to understand them, especially for the purposes of adaptation to climate change and for engineering design. So the normal strategy when interested in how something will be affected by climate change is to turn to climate models, because these are the tools we usually use to make climate change projections. But unfortunately, climate models don't represent near surface wind speeds very well, especially extreme near surface wind speeds, in part because of their coarse resolution. And so I'm just showing an example of this for just one grid cell in Toronto. So the black curve is the probability distribution of near surface wind speeds for observations. The green's from AR5 reanalysis, and the blue is from the CSM large ensemble. So you can see that the two numerical model products have a much weaker right tail than the observation. So they're really not representing these extreme near surface wind speeds. But not all is necessarily lost. This is going to lead us to ask, how do climate models represent the large scale drivers of extreme wind speeds? Because we expect they may be able to represent larger scale processes better than fine scale processes that affect near surface wind speeds. And then also how the representation of these large scale drivers of extreme winds change with refined resolution. So what I'm going to do is I'm going to use the observations to identify extreme winds in several Canadian cities in the historical record, identify which of those are captured as extremes in the AR5 reanalysis wind speeds, and then plot composite maps of the sea level pressure and 300 hectopascal wind patterns to identify large-scale circulation patterns that are characteristic of these extreme near surface winds under the present climate. We're also going to separate these events based off of the local wind direction, because we found that these large-scale patterns vary with the local wind direction, like I'll show, as well as the agreement between the CESM simulations and the reanalysis also depends on this local wind direction because of the different patterns. So yeah, I alluded to that, but we're going to assess how these synoptic patterns are represented in CESM, and then how regionally refined resolution might improve these patterns. So these are the suite of CESM simulations that we're going to use. Of most interest for the refined resolution is this variable resolution CESM simulation we have, where the resolution goes from about 1 degree over most of the globe down to about 7 kilometers over southern Ontario. It's this time slice type simulation. So the SSTs are prescribed, and their other atmospheric forcing is constant for the year 2000 conditions. We have an identical simulation to this that uses uniform 1 degree resolution over the globe, as well as the same spectral element dynamical core that's used in VRCESM. And then we also compare the results to those for the CES and one large ensemble as a well vetted publicly available reference. Right. So these are what the sea level pressure patterns look like for extreme events in Toronto, both for southwesterly extreme winds and for northeasterly extreme winds. So southwesterly is the most common wind direction for extreme winds in Toronto and generally in the broader Great Lakes region. And you can see here, all three of the CSM simulations do a really good job at representing these patterns. So the refined resolution is not really adding that much value. Where the refined resolution is adding value is for these northeasterly extreme events, where we see that there's really strong ageostrophic circulation because of this sort of tilted high low pressure dipole pattern. And the tilt of that pattern is better represented in their VRCESM. So we're seeing that for these less common events, but where ageostrophic circulations are really important and really strong, the refined resolution is adding value there. And just to show for sort of all general cases, these are some Taylor diagrams for the sea level pressure composites for a bunch of Canadian cities from the 4 different wind directions. And you can see that these markers are kind of clustered down toward the area of better agreement for VRCESM. There isn't really improvement for these cities in Western Canada, Vancouver and Calgary, but since those aren't anywhere near our refined domain, we don't expect to see improvement there. These are the composites for the 300 hectopascal winds. I'm running out of time, so I'm going very quickly. But the essential point here is that it looks like CESM is underestimating the magnitude of these jet streak patterns that we see, which is the sort of local maxima and the wind speed here. And our one question we were asking is, are the models lacking strong jet streaks, or are they underestimating the strength of the relationship? Since I'm almost out of time, the story is basically there are indeed strong jet streaks in CESM, but with the refined resolution, it seems like we get a more or least stronger relationships between the upper level winds and the surface winds. And that's true also for non-extreme winds. So here are the key points. Essentially, the idea is that when there's better agreement between the model and reanalysis, we feel that statistical downscaling of extreme winds could be appropriate based off these large scale drivers. But for cases where there's poor agreement, such as in Western Canada, for example, dynamical downscaling might be necessary in order for credible representation of these large-scale patterns. And we demonstrated how it can improve the representation for these events in Southern Ontario. So thank you.
Thank you. The next presentation is by Dr. Ishuko. It's about hydrometeorological real-time forecasting framework for flash flood early warning system development.
Sorry.
Yes, sir.
Thank you, Dr. Nayak, for introduction. So today I talk about hydrometeorological real-time forecasting framework for flash flood early warning system development, which can warn people in society of flood incoming to their houses, maybe some hours in advance before the flood. So integrated hydrometeorological modeling framework we propose in this study, and then we want to implement it into early warning system in Chugoku region of Japan. As written here, we did analysis for 7 rivers, as written here on the figure 1. And for the 2018 July extreme rainfall event. And the schematic diagram of the integrated model is on the figure 2, a meteorological deterministic forecast forced into hydrological model, this physically distributed model. And then this information can be useful for flash flood early warning system. So the hypothesis is that the ensemble hydrometeorological parameter calibration approach that is posted for tomorrow morning at 9 a.m. in hydrological session, then when we this is developed, calibration is developed using observed data, but when we change to meteorological forecast in real time, then we calculate how much lead times before the peak discharge can we get accurate results. And keyword is ensemble hydrological parameter calibration. Ensemble fluid forecast is in literature used usually with meaning that meteorological forecast is ensemble. But in this case, hydrological forecast is ensemble, which means like hyper calibration of hydrological model. And then left figure 3 is two a WRF model forced by ERA5 30 kilometer and second one, the right column, GRF5 55 kilometer. Just the output of this study domain shown in previous slide, and then some of these rainfall amounts are comparable of each other and reasonable amounts, but then also spatio-temporal and spatio-temporal distribution is also needed to be satisfied to be accurate result of hydrological forecasting. And for Takahashi river discharge, right figure is from 4 hours, the top one, until every next 6 hours until 22 hours forecast of the hydrograph, which means ensemble forecast. That there was 6 hydrological forecasts, and mean ensemble of them is shown here. So these results are showing quite good forecast for up to 22 hours for Takahashi river basis for river discharge. And then so this is magnitude is 10,000 meter cube per second. Then all 7 rivers together, to not show one by one, but to show all together, give discharge of fresh water into the ocean about 30,000 meter cube per second. And this is reproducibility of 5 hours lead time and 29 hours lead time. And in between, there is some in-between results also. So we can see that 5-hour lead time is very, very well reproduced with very high NSE 0.98 or 0.90, 0.94. And then, so this confirms the hypothesis that we can do quite accurate prediction for 20 hours lead time, up to 20 hours lead time. So this estimations of all rivers freshwater budget is very useful also for coastal engineers and coastal sea dynamics modeling and pollution transport and many other things when modeled properly. And then we expect our methodology can be very, very conveniently replicated in well-gauged basins, but the approach of the ensemble hydrological calibration can be reused also where data is less available, but then applying some different methodology, but similar approach. So the most important output is approach. And then, so this is the summary. In the first lines shows how this study is developed from previous studies until today. And then our recommendation is that for the hydrological calibration, we need to define similarity rainfall patterns from some past events. That's more explained in the poster tomorrow for hydrological part. And then second recommendation is that ensemble hydrological parameter calibration decrease uncertainty and increase accuracy. And that approach using can enable developing of robust real-time flash flood forecasting early warning system. So thank you very much for your attention.
Okay, thank you, Dr. Isiko. Our next presentation is by Dr. Ima. The talk is about meteorological drivers and local impacts of the exceptional 2020 Labor Day weather event over Western North America.
Thank you. Before I begin, I would like to acknowledge my co-authors at Portland State University and the National Center for Atmospheric Research. In early September 2020, Oregon experienced an unprecedented wildfire event where extremely anomalous weather patterns led to the rapid spread of several large wildfires across the state, with much of this wildfire activity occurring in the Oregon Cascade region. These wildfires ultimately burned over 1 million acres across the state, and as they were doing so, they produced large amounts of wildfire smoke that blanketed the region and led to a period of prolonged surface level smoke. One of the regions that was largely impacted by the smoke production was Portland, Oregon, which sits within the Willamette Valley. And as the smoke was produced, it settled into the valley and was met with stagnant weather conditions that ultimately resulted in several consecutive days of hazardous air quality in Portland, which you can clearly see from the air quality indices during this time circled in red. And the Pacific Northwest was not the only region that was impacted during this time. The same large-scale weather system that was associated with driving the wildfires in the West also led to an early season snowstorm in parts of Utah and Colorado, where there were record-breaking drops in precipitation or drops in temperature and record precipitation fell. So clearly this was an impactful event across most of the Western United States. So for this study, we're aiming to determine the meteorological drivers of this event. And in order to do that, first we look at MERIT-2 reanalysis data for the Labor Day wildfire event, which we have defined as the 3-day period from September 6th through 8th, 2020. And here in the figure, you can see the first day, September 6th in the first row, followed by the second day in the middle row and the last day in the bottom row. Here we have 500 millibar geopotential heights. And you can see at the beginning of the event, there is a very strong and broad ridge over most of the Western United States. And as the event progresses, we see the development of a blocking pattern, most prominently seen in the bottom right map. This blocking pattern is set up to where there's a very strong ridge west of the Pacific coast and a similarly strong trough east over Utah and Colorado. These blocking patterns are known to be very persistent and stable, and this ultimately resulted in very dry and warm conditions in the Pacific Northwest and also led to those early season snowstorms in Utah and Colorado that I mentioned earlier. Next, we look at sea level pressure. As the event progresses, we see the development of a very strong pressure gradient with higher pressure to the north and lower pressure to the south. And patterns like this are known to drive offshore winds, and that's ultimately what happened during this event. So dry continental air was transported into the Pacific Northwest due to these easterly winds. From potential temperature on the 2 PVU surface, we can see anticyclonic Rossby wave breaking occurring on the eastern side of the ridge, as pointed out by that red arrow. And lastly, we look at a high split air parcel backward trajectory for a region that was largely impacted by the wildfires, and that was Detroit, Oregon. And the intention behind this is to determine the origin of the air mass that existed in the Pacific Northwest during this time. Here we see on the leftmost map during the first day of the event, the air parcels are originating somewhat locally to the region, all within the state of Oregon. And if we move to the middle map and zoom out quite a bit, we can see this large shift in air parcel origination, where by the end of the day, as you can see by that red air parcel track, air is no longer coming from a localized region, is actually in fact coming from northwestern Canada. And I should mention that these are 24-hour-long air parcel trajectories. And then on the furthest right map, we can see on the last day of the event, all of these air parcels are coming from northwestern Canada, more than 4,000 meters above the surface. And this dry and cold air is descending down to its destination, and as it is doing such, it is warming adiabatically. So in conclusion, this was a highly anomalous weather event that had widespread impacts across the Western United States, and was mainly due to several meteorological conditions that created an environment that was conducive to the spreading of wildfires, and additionally, that early season snowstorm in Utah and Colorado. Some of those drivers include a blocking pattern, a strong pressure gradient, and a dry air mass that was from Canada. Thank you very much.
Thank you, Dr. Ima. Next is by Dr. Leahy. It's about origin of extreme cold front temperature constructs, the case of Australian fires.
Hi. Kind of connected to the last talk I just saw. Thanks. So my name is Leahy. I'm going to present work that I've been doing with Sheila Rave-Rubin at the Weizmann Institute in Israel. And I'm going to show you about exceptional fronts, or very strong fronts that drive historical fires in Southeast Australia. How do I, not that one. There you go. Okay, so Southeast Australia is a very fire-prone area. And it has a very typical fire weather system. So a low pressure system to the south or southwest with a high pressure system to the east. And usually there's another high pressure system to the west. And with the main factor that controls the spread of the fire is the passage of the cold front. So after the wind changes, the spread of the fire becomes much stronger and larger. And many of the historical fires have been connected to these extreme fronts or the strong fronts with a strong temperature drop. So I'm going to show you one case, the Black Saturday fires in 2009. It was a very large fire with many casualties, but it was also extreme in many other ways. It had one of the most extreme heat waves before the passage of the front, so in the warm sector of the cyclone. And it had one of the strongest 1% of the cold anomalies that arrived after the front itself. So both of these extremes actually caused a very strong temperature drop. So in this work, we wanted to look at what led to the formation of this very extreme front. And we looked at we took a Lagrangian approach and we looked at traced the potential temperature anomaly along the trajectories themselves. So we took trajectories for 96 hours from near the surface, and we looked at the anomalies themselves. So this is just an example of the anomalies at the endpoint near the surface. And we can see that before the cold front, they increase and reach very high levels. And then after the cold front passes, of course, they decrease and we get negative anomalies coming into the region. So if I just look at two snapshots of the trajectories from the warm sector and the cold sector. So in the warm sector, we find two distinct airstreams. Now, these trajectories are colored by pressure. So they show the height of the air mass. So we have easterlies that are coming from lower levels and arriving into the area near the surface. And we have westerlies that are descending into the area. After the cold front, and all of these trajectories in the warm sector are bringing warm anomalies, as we saw before. And in the cold sector, we have a change of the wind, and we have a dry intrusion that's arriving into the area, bringing cold air down into the surface. And we also have something that's not really evident in this figure, but I'm going to show you has a lower level flow that's going beneath these trajectories and interacting with the surface. So we decompose the trajectories into three parts. An initial anomaly at the origin, some diabatic change, heating or cooling that's affecting the air mass, and a transport of climatology that's driven adiabatically. So if we look at the evolution of these components, and this is just this is what you see in the bar plot on the right. And if we start from the left side, this is the warm sector. So we have the initial anomaly in the green, diabatic heating in the yellow, and the blue is the climatologically transported air. And we see that first we have diabatic heating, diabatic heating that's coming in the easterlies, the flow that's closer to the surface. And we have transport of climatologically warmer air that's coming from the upper levels, but is also bringing with it this warm initial anomaly that exists there in the air. If we go to the cold sector, we see that the transport is now negative, and it's actually coming from the low level flow that I mentioned before across the potential temperature gradient. And it's counterbalanced by this diabatic heating from surface fluxes of the flow. The descending air, the dry intrusion that we see in the area is actually bringing cold anomalies now into the area, and they're affecting the anomaly that we see. If I try to sum up everything together, so this is the climatology of potential temperature in two cross sections with height, so longitude on the left and latitude on the right. And we see that actually the potential temperature anomaly that we see in the warm sector is a result of descending air streams that are bringing with them warmer potential temperature, but also a warm anomaly that's arriving into the area. And in the cold sector, we have this dry intrusion that's descending along isentropic surfaces and bringing with it especially a negative cold anomaly that's arriving. And now I wrote everything down. I just want to point out that's really interesting that we found these descending air streams that they're stronger in the cold sector, but they're meaningful in the warm sector also, that are bringing the anomalies either warm or cold to both sides. And we see that all these three contributions are really important, and they change directions along the passage. I have more information and more things to say. If anybody had any questions, feel free to, I'll be happy to talk. And thank you very much for your time.
Thank you, Dr. Lee. So if you have any questions, you can write down in the chat box. I can see there are some questions already came. So I will take one by one after the sessions finished. Okay. So the next is virtual by Dr. Wang, which is about prevailing the spatiotemporal properties of the mesoscale convective systems most conductive to the precipitation extremes during the 2021-2022 Malaysian floods. Okay, please.
Hello, everyone. My name is Jingyu Wang. I'm assistant professor at National Institute of Education, Nanyang Technological University, Singapore. Today, I want to share some of my understanding of the 2021-2022 Malaysia flood. I want to thank my collaborators, Professor Edward Park, Professor Xianfeng Wang, and PhD student Luo Jiedong. The 2021-2022 Malaysia flood is marked as once-in-a-century event, which caused a total of 54 deaths, hundreds of thousands of displacements, and economic loss up to $1.5 billion. The series of the flooding consists of two major parts. One is over East Malaysia, which was mainly caused by the overpass of Super Typhoon Rai, and the other occurred over the Peninsula Malaysia, which is associated with the landfall of strong tropical depression. The latter one caused a higher casualty and economic loss. Therefore, it is the focus of this study. As shown in the hazard summary map on the left, the state of Selangor and Penang suffered most from the event. However, they demonstrate different flooding scenes. The former is more like urban flooding, but the latter has a view of suburban flooding. We want to explore the source of the flooding water. Here we check two daily precipitation products. One is the ERE5 reanalysis, the other is the CHIRPS observation. As shown in the upper left panel, both data sites show the major precipitation period occurs from December 16 to 18. Therefore, we constrain the study period to these 3 days. By comparing the event to the historical 3-day average precipitation in December, we found that severe anomalies dominate the entire peninsula. The black dots here denote the location where the grid exceeds the 99th percentile of its historical record. The black dots are mostly concentrated over the two regions. Region A represents the Selangor, Region B represents Penang. And both regions set their new record of heavy precipitation during the event. After confirming the timing and the location of the event, we want to further explore the systems that brought such extreme precipitation. By using FONG 2021 storm tracking algorithm, we identified two consecutive mesoscale convective systems, MCS, that have overpassed over the peninsula during the time window. Their evolution are shown in the animation, and their lifetime roughly follow a typical MCS pattern with different stages of initiation, genesis, mature, and dissipation. And you can tell that MCS2 immediately follows up when MCS1 dissipate and move out of the domain. The two MCS are labeled, but it is more important to understand under what condition such high precipitating MCS could occur. As shown in the figure on the left, two key drivers are identified, namely the mean sea level pressure, labeled with the contour lines, and the integrated water vapor transport, IVT, which are color shaded. Apparently, during this event, Peninsula Malaysia was directly influenced by a tropical depression. However, the moisture is not solely localized. There is a big portion transported from the Super Typhoon Rai. The magnitude of the long-range transport exceeds 300 kilograms per meter per second, which is above the threshold of 250 that is commonly used to define atmospheric river. In history, there are 78 out of 630 cases with mean sea level pressure lower than the 2021 event, and the number of cases is 16 with higher IVT. So the joint probability of the two drivers to coincide is around 0.3%, which translates to the occurrence rate of once in 300 years. The rationale is The low pressure center serves as the engine, and the moisture serves as the fuel. As shown in the bottom right panel, where the location of the historical lowest pressure center are marked with proportional symbols representing the IVT intensity. You can tell that such strong combination during the 2021 flood has never happened before. This is my email address. Thank you for your time. Please contact me with any questions.
Thank you, Dr. Wang. So we have one presentation is missing. So the presenter is telling it is uploaded, but we are not getting it here. So let's see.
They don't have it, the speaker ready, there's no 1525. It's supposed to be 1525, saying nothing. I recall, I've asked them 3 times already, they don't have anything. So I can tell you.
Okay, so if this is not, we didn't find the pre-recorded video of that presenter, so we'll skip that. If it's possible, we can allot it in the next session. In the next session, it is one presenter is not able to attend, so we can adjust there. So Ms. Soumya, if you're listening, then please sort it out. Go to the speaker ready room and make available your video or your materials. You can you are attending in person, so you can present here. Okay. So now we like to take the questions. So we have 15 minutes. So I like to ask the participants, please, if you have any questions to any speakers, please, you can ask. So any questions to any speakers? Okay, please. Okay, you can ask anytime. So in that time, in the meantime, I am taking some questions asked in online. So first question is to Dr. Muhammad. Yes, please. So the question is about, yeah, thank you for the nice talk. How is volatility defined in your studies?
How is it defined?
Yeah.
Okay, yeah. So the question is how volatility is defined. It's basically very straightforward. It's essentially the absolute difference in daily maximum temperature between 2 consecutive days. And the reason why I'm using daily maximum temperature rather than daily mean temperature is because a lot of the recent studies in epidemiology show that daily maximum temperature is far more important when it comes to human health than daily mean temperature.
Okay. Yeah. Okay. Thank you. I think you answered the question. Okay. The next question is to Dr. Christiana. The question is, yes. Are changes in wait times and clustering linked to the changes in spatial scales of the convecting systems?
That's a good question. The short answer is, I don't know, but I'm working on some extension, looking also at spatial extremes where we can see how the spatial structure changes in the future, whether it extends or not. And so that might be something for future research. But right now, I don't know, because I also haven't looked. Right now, I only looked at total precipitation, but of course, ERA 5 and CSM would also allow me to look at large-scale precipitation or convective precipitation, which probably would then allow me to answer this question.
Okay, thank you. So any other questions from the participants?